So what is Kelvin Probe Force Microscopy? It's not a temperature measuring microscopy art. For that you have scanning thermal microscopy. But with Kelvin, you image the sample potential distribution without being directly in electrical tip sample contact. In generally, it's done in dynamic mode, either directly or in the so-called contour following mode. I'll get back to that later in the slides. What can you do with it? You can look at conducting samples and image the contact potential difference between the tip and the sample, also called Kelvin potential, hence the name, or work function, and that gives you a material contrast on your sample. For example, to identify material domains in a metal alloy, as you see here on the right. This is also an image that Dalia showed last week. It's a stainless steel with some ferromagnetic and non-ferromagnetic parts in it, and they have clearly a different contact potential. It can also be used for 2D materials on graphene sheets or molybdenum disulfide, or totally different if you have a metallic surface which is partly contacted and which might have where you're not sure whether every part is contacted. With Kelvin probe microscopy, you can also measure contacted electrodes on a surface. On insulating samples, you can also measure with Kelvin probe microscopy, and you measure then the charge landscape or potential landscape of a surface. Here you see an example of a gallium arsenide sample with an oxide, a native oxide surface layer. And in this layer, by putting the AFM tip on, apply a pulse of plus 10 volts, electrons will pull away from the surface, and if this surface is imaged afterwards in Kelvin probe microscopy, you nicely can see where the charge have built up in this oxide layer. Now, I apologize for the equations. Normally, it's not nice to have equations in a presentation, but I think here it's very helpful to understand the way we measure it. If you have two conductive objects, there is an electrical force between them based on the capacity. If there is a capacity between the conductors and you change the distance between the conductors, the capacity is changing, and this capacity gradient together with the voltage difference between the plates gives you an attractive force. What we can learn from this equation is that it depends on the difference in tip and sample voltage squared. That means it doesn't matter whether the tip voltage or the sample voltage is higher. And because of the minus sign, it's always an attractive force between the two metal bodies, unless there is no potential difference. Then the force, attractive electrostatic force, is zero. How do we measure that? What we do is we don't apply a constant voltage to the tip, but we apply a combination of a constant voltage plus an oscillating and AC voltage to the cantilever. And that would look for the potential like this. And you can do that with a frequency F. And if you fill that into the equation that we had on the last slide, you get here the DC components, the sample voltage, the DC tip voltage, and there the AC voltage. It's exactly the same equation as before. There's a minus missing, but that should make the big difference. You see that if you write that out, you get three different terms: a constant term on the left, a term in the middle in orange, that's the main term we are working with today, a term that depends on this frequency F, an oscillation with frequency F, that depends on the voltage difference between the tip and the sample. And then there is also a squared a dependence, or a two times the frequency applied frequency component there in the end. That depends on the amplitude of the AC voltage. But here you see again, if the tip voltage is the constant, or if the constant part of the tip voltage is equal to the sample voltage, this term is disappearing. And what you can also notice here is this term is not squared anymore. We now go to the next slide, and then you see here in the middle what happens if my DC voltage on the tip is exactly equal as the sample voltage, here denoted by the red line. Then you have this AC voltage around it. At those points where the tip voltage crosses the sample voltage, there is zero electrostatic force. But then if the tip voltage higher or lower, you get an attractive force. And what you see here is I only have the 2 times the frequency component left. This sign here at the bottom oscillates 2 times, while the applied voltage only oscillates a single time. If I now apply a lower DC voltage, so my blue curve is below the red curve, you see that there is a large oscillation now also in frequency at the same frequency of the voltage oscillation. They are close to the maximum in the tip voltage. There is only a very small difference with the sample voltage, and my attractive force is close to 0. And there at the lowest voltage part, I have a very high attractive force. And what you see here, a low voltage gives a low force. Here on the right, we see almost the opposite behavior. The tip voltage is above the sample voltage. There at the lowest part now of the tip voltage, the voltage is almost equal, and there I have 0 force. And here at the highest point, I have the largest discrepancy, so I have the largest attractive force here. And what you see here, that they are in counter phase. So high voltage gives the low force here, the strongest attractive force. So here you are in phase, here you are in counter phase, and this is something we can use in a feedback loop, that we can adjust this DC voltage so that we always stay around the sample voltage. And that tells us also at the same time that if I am here, then I know that my tip voltage equals the sample voltage. So by monitoring the DC voltage, I get a measure of my local sample voltage. And that is the idea behind the KPFM measurements that we put in our AFM. How do we implement it? We generally work in dynamic mode. So we have a shaker piezo that oscillates the cantilever at its resonance or close to its resonance. And that gives us our first feedback loop for the topography, just as you normally have in dynamic mode measurements. That is here at around 150 kilohertz. Then, and here you see it in the schedule, a shaker piezo is being oscillated at a frequency F1. Then at the same time, we have the DC offset voltage plus the modulation voltage at a frequency F2 oscillated through a conductive coating that is on the cantilever. And that is at a much lower frequency, well below the resonance frequency. And that we monitor separately with a second lock-in amplifier, and that gives us the contact potential difference, or the KPFM signal. Both lock-in amplifiers are integrated into the AFM controller, so you don't need any additional external electronics to do this experiment. If you look into KPFM and you look into literature, you will find 2 main streams, one going for single pass and one going for dual pass measurements. And in the single pass measurements, you measure the sample in dynamic mode at the resonance frequency, And while you do that, you really, at the same time, apply this AC voltage and you look at a different frequency for this KPFM signal. And you get both signals at the same time. So you only have to scan your sample once to get both your topography and your KPFM signal. So it's relatively fast. It's the same speed as your imaging speed. Because you're in tapping feedback, you have a very short tip sample distance, and that gives you a very high sensitivity and a very high resolution. It can only performed in dynamic mode, because if the tip is in static mode on the surface, it will not oscillate so well when you apply an AC voltage to it. In the dual pass mode, what you do is you make a first scan of the topography. You go back, then you lift up the tip, and following the same contour as that was measured in the topography measurement, you move above the sample. And while doing this measurement, you can measure the contact potential difference of the sample without being in contact. It reduces some topography artifacts in the KPFM signal. It generally has a little bit less noise, but it is inherently slower. You have to scan each scan line twice. In addition, often you are a bit further away from the sample to prevent a tip crash, so you lose a little bit of sensitivity and you lose a little bit of resolution. You can partly reduce this because in the second pass, you can turn off the dynamic mode excitation to get a much smaller oscillation of the tip and get closer to the sample. It additionally also helps that you have less background for the second lock-in. Though generally, if the bandwidth is set correctly, that crosstalk is very minimal. Finally, if you like, you can still do the KPFM excitation at the cantilever resonance frequency to get a higher potential sensitivity. And if you would like, but I haven't found many useful applications for that, the topography in the first scan can also be acquired in static mode. So let's get to today's experiment. Today's experiment, I'm using the CoreAFM, which you see here. And this CoreAFM has a wide range of application possibilities. And for the KPFM experiment, I'm using, of course, the core, which has active damping, static, dynamic, phase imaging modes present, also lateral force, standard spectroscopy and lithography. That's all standard available in the CoreAFM. In addition, I have the standard conductive AFM mode so that I can work with conductive cantilevers. And I have the KPFM mode option that makes this mode available in the software. Optional modes that I'm using now is the EFM sample kit. I'll show that on the next slide. And for contour following in dual pass, you need the advanced dual scan option. But as I said, this is optional. If you work in single scan measurements, single pass measurements, then you don't need this option. Finally, but not relevant for the KPFM, the CoreAFM is standing in an acoustic enclosure to reduce acoustic noise so I can freely talk while doing my experiments. As said, today's sample is the EFM mode kit that we have. And in the EFM mode kit, there is a sample. It's mounted on a metal disc. The top is made conductively connected to this disc with a two-component epoxy cement. And then this is placed on a conductive sample holder that is grounded to the scan head. The sample has a gold coating, and on this gold coating, there is aluminum pedestals, and these two materials have a different work function. So we do expect to get different tip contact potential difference when scanning either on the gold or on the aluminum. Cantilevers in the mode kit, and the one that I'm also using today is Electri Multi 75 or Multi E75. Cantilevers from budget sensors have a resonance frequency around 75 kilohertz, and they are suitable to do this kind of experiments. So let's get started, and let's switch to the AFM software. And here you see the software. I already activated the KPFM, so you see here also the tip voltage, which is the output of it. And I used before a parameter file to load it. And you see I have here two parameter files for KPFM. I have a normal one and a dual pass one, so I can store every parameter set that I want to use for an experiment. I can save that and then load it for later use again, so that I don't have to make all the adjustment every time. Shortly about parameter set, we are working in air. I'm working in the phase contrast mode. The cantilever as said is the Multi 75E or Electri 75, it's also called. And for the KPFM, I go there into the More button, and under operating mode, I find there that I have enabled the second lock-in amplifier. There is KPFM in. You can also just have the second login activated for other experiments, or a PFM response, the piezo response microscopy. So we are talking about KPFM today, so it's on KPFM. I have the amplitude and the frequency of my oscillation. So the frequency chosen well below the resonance frequency of the cantilever. The parameters of the second lock-in amplifier, and the main one is the reference phase, but you don't have to worry too much about it. There is just a push button way to set this reference phase. And the reference phase is set to get the maximum response of this lock-in signal when you change the tip voltage. To do this, I first want to approach to the surface, and here on the video screen you see the cantilever, its shadow, the sample of the structure. It has a repetition of about 5 micrometers, and you nicely see that in the top view image. And if I now approach the sample, it will shortly do a fine sweep to check whether my resonance frequency is still where it's supposed to be. It would also immediately detect if the cantilever would be broken off, or if you had changed cantilever type, it would give notice there. Nicely see the focus changing on the sample as the cantilever is going to the sample. And now it's already at the surface. In our software, we have different options here. Now we are looking at the video. I can look at the gallery to look at the files I saved, but I also have a monitoring. Where I liken a scope, I can look at different signals that are occurring in the AFM. I look at the lock-in amplitude, phase, and here the second lock-in amplifier, the X contribution. And now I'm going to optimize the phase, and what it will do is it will apply a tip voltage ramp, which you see there, by the way, in the bottom trace. And while it does that, you can see how the lock-in is responding. Based on this response, it knows what the optimal phase is. So let's run this. So you see there is the voltage running. The lock-in was also responding and slightly modified the phase. It's almost the same as before. And this is all it is, what you have to do about setting the reference phase. Controller in the end, we want to add a DC voltage that is just like with AFM. Again, the I gain is the most important one. How fast do you want the DC voltage to get to reach the sample voltage? If it's too fast, it's getting noisy. If it's too slow, it's getting sluggish. So we are at the surface, and now I can actually immediately start imaging. And what we see here in the left is the topography. And the pedestals are clearly there, the high parts, with in between the gold. They are the amplitude response. And here now at the right, the dip voltage. I don't find, in this case, the amplitude so interesting. So let me put here the dip voltage so that I have it next to the topography. And now I can look here how topography and dip voltage correlate. You see here there is the background there is a bit darker between the dots. That's the background correction. It's standing on line fit. I can, of course, change that in both cases to raw data. And if it rescales afterwards, you see that these dark bands where the dots are will be gone. We'll leave this scanning now for a while, and I will show you a data that I recorded this morning. And that is, let me see, there. So what you see here is Mountain SPIP software, which I used to load the data in. And it's the same grading that I measured earlier today. Left top topography, left bottom the dip voltage, and here you see the overlay. Like you would expect, you can rotate this. And what is very nice about the Mountain SPIP software is that here in the right side, you have all the steps that you did to your sample. So what I can, for example, go here in the topography, I can see I did a plane tilt, and there I did also a line by line tilt, and I can look, okay, how was the line tilt done? It automatically looked for structures above the background to exclude that. And if I, for example, would not do that, you see I get immediately these artifacts in the topography that are not real. So if I do this automatic exclusion, I nicely get my topography like I expect it to be. Also allows you to have scaling just as you want it. So I have here like nice round numbers, minus 450 plus 350. And if I do multiple samples, I can always take care that I have the same scaling for every sample so that you can easier compare your data. And what is very powerful for me is if I make a report and suddenly somebody tells me I want to have a different color, I want to have a different scaling, I can just open my document, click on a single processing step, and just modify that processing step without having to reload the data from the start and redo the complete processing. It has remembered all the processing steps with the processing parameters that I used. So that a little bit about the data processing that you can do with KPFM so that you can nicely make overlays, that you can better correlate the potential with the topography. So let me go back to the AFM software. So we are already over half of it. And very interesting here is, for example, you see here now some dots where in the topography they look quite normal, but in the voltage they are deviating. They have some different properties. So apparently there is some material deposition or so on top of these surfaces. So this is now all run in the single pass mode. So tip voltage and topography are measured at the same time. I can stop this measurement now. And if you say, okay, the data are still good, you can still capture it. And now this partially imaged data are in the gallery. As said before, there are two flavors to the KPFM. You can do it in single run or you can do it in dual run. Single run, that's the standard imaging condition that you have. And here you can have dual scan or interlaced, that you have a normal scan forward and a lift mode on the way back. Or what's often used for MFM is that you only measure the second scan. Gives you an increase in speed if the topography is not containing much information. So I'll select dual scan. And once the dual scan is activated, I can here enable the contour mode so that it remembers the topography of my first time that I scanned over a scan line and apply that same topography over the lift. Let's give it a bit of a height, a lift height. In the second run, in the first run, I have an 800 millivolt amplitude. Now in the second run, I will make it smaller. I don't want it to make it totally zero, because if I have some amplitude left, I can immediately see whether my tip is nicely away from the surface or not. Dark mode, I can switch off the laser if I like in the second scan. And I want to have the tip voltage control in the second scan. That is now set up. It has rearranged these display fields automatically. So again, topography, amplitude, phase. And since we are now scanning twice, the area you have there, the amplitude of the second scan, the phase of the second scan. And here you have the tip voltage of the first, and there I can also have then the tip voltage of the second scan. And if I now rescan this area, it scans each scan line twice. So now it has the first scan line coming up with the topography, and here the tip voltage there and there of the second line. I'm now at a lift height of 300 nanometers, and you immediately see that the signal is much more noisier. It's a smaller signal. And this I can now change by reducing the lift height. Since I'm working with a free amplitude before of 800 millivolts, 80 millivolts is much smaller, so I can even go here down to 0 nanometers. And when I do that, you will immediately see an increase in signal of the second scan. So we are now much closer to the surface, and you see that. What you also see is that you start to see the edges in the topography. That means I'm now a little bit too close. So I can now try to perhaps lift it by 25 nanometers, see whether that's enough. Yes, and now there's still a little bit to see in the phase, but now the amplitude hardly contains any information, so I'm hardly touching the surface now. And what you also immediately say is that my scanning is going much slower. I still get my tip voltage in the first scan, but I now also get my tip voltage in the second scan. And while running this, I think we can just start the question and answer session, and we can just look how the signal is progressing while I answer your questions.
Right, thank you, Patrick. That was a cool presentation, very interesting. Not the simplest mode, in my opinion, but it seems that the software does help quite a lot with automatic functions and if you can load the parameter files. Which brings me to the first question we have is, can you send me or can I have a parameter file for KPFM?
Yes, of course. So if you want help with setting up a mode, whether it's now the KPFM or spectroscopy or another mode, we have parameter files for many of the modes. And otherwise, we can help you constructing one, and just contact us, and then we'll help you together with our local partners to get the parameter files for your setup.
That must make things easier. And there's a question about in the SPIP software, the image you showed there on the upper left was a pedestal with a kind of a spike. And the question is, what's that spike?
Yes, okay, let me change the screen to that one. So you're talking here about the left top here, the yellow dot. There is a contamination on the surface, and that contamination is very high. You see it not only in the topography, you also see it in the potential measurements, that also the potential is that different from the surrounding potential. So it means it has likely a different material composition than the gold or the aluminum, and hence gives both not only a different topography, but also a different potential. So for a publication, I would move the sample a little bit to get rid of that contamination and find a cleaner area of the sample. But I think for the purpose of showing data and how to process data, it's okay that there is some contaminations on it. That's
okay.
just showing how live is.
Yes, definitely. Good to see something like that as well, so you're not surprised when you actually do your own measurements. So the next question, I couldn't see how much voltage you applied to the tip to zero, the VDC VAC component. How did you decide that?
So let me go here to the operating mode, and I have to share the other screen again. Share. So I hope you can see the SPM parameters window. What you see here, I'm applying a voltage of 2 volts. That's a decent value. I can make it smaller. The signal gets a bit noisier, but it also has a smaller range, so you can get a bit better lateral resolution. If I make it bigger, I get a better signal to noise ratio, but I might also lose some resolution. So that's about the amplitude choice, and the applied amount of DC voltage. I can read that from this graph. I can put it to raw data, and that is not set by me. That is automatically set by the controller. So the controller decides that on the gold, I need about -400 millivolts, and if I'm on the aluminum dots, I rather need, what is it, about -80 or -60 millivolts. So that is set. That's determined by the system automatically. I have not so much influence on that.
But the 2 volts you chose is just because of experience. That's where you start.
So we can definitely start. Continue with 1 volt and see what's happening there. And see it's giving roughly the same kind of data. If you look accurately, the noise level might change a bit, and the resolution might change a little bit.
Okay, so you just try out until you have a optimal.
Yes.
Okay. Next question. Is there anything special about the cantilever holder, and how easy is it to connect the voltage supply to the tip?
Okay, this is indeed a special cantilever holder that comes with the standard conductive mode option. And that cantilever holder takes care that you have an electrical connection to your cantilever. So you don't have to connect anything else. The moment that you put your cantilever on the scan head, it automatically will make the electrical connection. And then no fuzzle with wires or so, that is then done. Of course, the cantilever needs to be conductive. It needs a conductive layer on the front. And whether that is a gold layer or a platinum iridium layer or a platinum silicide or conductive diamond-like coating, I mean, that's all possible. That should not really matter a lot for the KPFM data.
Is the holder part of the mode kit?
Yes, it's part of the standard conductive mode kit.
Okay, so if you buy that, you basically have everything you need.
Yes.
And then the next question, can you get the work function from the KPFM measurement?
That's a good question. It's an often asked question, and in theory, yes. In practice, it's cumbersome. To get the work function of a material, you need clean surfaces. We are working here in ambient, and in ambient, there is always a water layer on top. There is always, there can always be some oxidation, there can be contaminations, and these influence the measured contact potential difference between the tip and the sample. You can try to get it better quantitative. You can try to work in a glove box to get rid of the oxygen and to get a much lower humidity. And then you need somehow to characterize your tip first. A suitable material for that would be HOPG, freshly cleaved, and then make a contact potential difference measurement on that sample. Then you change to the sample that you want to measure and measure the contact potential of that sample and compare it with the one from the HOPG. But still, if the tip picks up some contamination from the surface, it will change the potential difference that you measure. So it's certainly not trivial to do it in ambient conditions.
Okay. The next question is, can you run your system in a way that it will apply increasing sample bias, for example, -1 volt to +1 volt, while it is live scanning to see how the surface potential changes?
No, that is not directly possible. So you can do voltage spectroscopy. So if you go to the spectroscopy tab here, let me see, there is the spectroscopy. I can select here to drive the tip voltage and measure how the lock-in is changing as function of the tip voltage, and then where the lock-in contribution is 0, I know that my tip voltage equals the sample voltage. And if you then make a map of points, you can do that on many places in the sample and measure like that the tip of the sample potential at different positions, but it's time consuming compared to the normal imaging mode. So it's difficult to get the same lateral resolution that you have here. But to probe single position, yes, this is definitely there, it's possible.
Okay, hope that answered your question. The next is, Is there a BNC port or some other port on the instrument where one can take the raw data from either lock-in and watch it on a separate laboratory oscilloscope?
Yes. So we have here a signal access module that is connected to the controller, and there you have also monitor exits that give out the signal that is given out, that you can select different signals to put out to an external source. I have to say there, the lock-in 2X component will be digitalized, will have been processed through the controller before it's given out, so that's not the direct analog signal. But of course, the tip voltage that is used in feedback, that comes anyway from the controller, so that is also given out on, you can give that out on a monitor.
Okay, thank you. So currently we have no further questions in the queue. So if anyone has a spontaneous question now, just please type it into the Q&A tab. While we wait, in case someone does have a question, I just want to let you know about a new white paper or application note on KPFM that we just published yesterday on our homepage. So you can find it if you go to nanosurf.com, click on applications, and it will be the first on the grid. It's called just KPFM. It doesn't necessarily have all new images. Some of the data is from past measurements we've done, but we've rewritten it, and hopefully it's a much nicer explanation of how it works and how the measurements that are shown in that app note were made. We do have another question. Can you excite the sample with a laser to see how the surface potential changes?
In principle, yes. I mean, we don't have a standard laser for that in the system, but either if it's a transparent sample, you can work on an inverted microscope, or with the Flex AFM, we have openings on the top through which you have access to not only to look through it, to have the top view, side view of the cantilever, but you can also couple light into there onto the sample.
Follow-up question, but we can couple blue laser, I assume.
I
Not
would
sure what's meant
yes.
by couple, but
I would say yes.
Okay. Okay, should we just give it another minute in case someone thinks of a question, or is there anything else you just want to point out at this point in time?
So what, yeah, you already mentioned the application note. So today I hardly went into the application of KPFM. I mainly focused on how it is operated and what you can do with the data afterwards. The application note that you mentioned gives several examples of applications of KPFM. That is 2D materials, graphene, molybdenum disulfide. It's also the stainless steel is in there, and gives you some more background information and ideas about the technique.
Cool. One more question came in. It's an interesting one. Have you imaged any biological systems for KPFM mode?
I think we have an application note actually on the web. I think they might have done KPFM. It was on bacteria, if I'm correct, but it was imaged in air. So KPFM works mainly in air. If you're talking about biological samples and want to measure in liquid, I'm not so sure whether KPFM is the right technique. There are some very exciting developments at the moment with SICM, in which you can actually measure the local charge distribution of a surface through a hollow pipette. That can be a fluid FM cantilever, but it can also be a glass pipette. But with KPFM, I'm not sure whether that works reliably, at least not in a watery solution that with a lot of ions in it that shield the surface charge.
Maybe we should have a session on FluidFM with KPFM then. There's another question. Can we use it for powder samples?
If you can prepare the sample well enough that the powders are nicely fixed on the surface, yes. It's of course then very interesting, what is the material of the powders? Are the powders conductive or not? And I think the trick there will be the preparation. It's certainly possible if you take a 2-component epoxy cement, put that on the surface. If you can cure it at room temperature, and just before it's cured, if you can add the powder substance to this epoxy silver to contact the powder, then you can measure it. If it's insulating powder particles with an insulating layer of tape in between, it may prove difficult to measure KPFM. What you still may be able to do is to switch off the KPFM feedback and just look at the lock-in response at the voltage, because voltage of insulating particles may well exceed the 10 volts that we have for the KPFM feedback.
Okay, here's another. Can you very basically describe the difference between EFM and KPFM?
Yes, so what you do with EFM is that you work at the resonance frequency of the cantilever, and it's very similar to MFM, or what is the subject of our next live web demo next week. And what you do there is that this attractive force that you create by the voltage, that of course also changes the resonance frequency of the cantilever. And that resonance frequency of the cantilever you can observe by a change in phase. What you do in EFM is that you measure this phase change when you scan over the surface. You have to do this in a dual scan mode, and if your sample is not very flat, you really need contour following for that. It's a very qualitative measurement, and you need to apply often quite some potential, DC offset potential, to the tip to get sufficient contrast between the different materials. On our website, you see an example where I use this technique on this very sample that we now measured with KPFM. With KPFM, you keep the voltage difference between the tip and the sample much smaller, at least the DC component of it. And that gives you a much better resolution than what you can get with the EFM data. And at least it's getting semi-quantitative towards the work function. Whereas the phase is much more difficult to quantify.